Okay, so in this video, I want to say how we compute the exact area underneath this curve y equals f of x. And again, I'm going to think of f of x as positive for now. Okay, so we saw in the last video that the area, if we're approximating the area by n rectangles, it's given by this formula. Each base is b minus a over n, and then the height is determined by the function value, the y value. Right, so we get this formula, and I can factor out b minus a over n because all of the bases are that, and then I just add up the heights like this. And so this approximation is an approximation using n rectangles. And if we want to get a better approximation, we can use more rectangles. So like if I'm using, say, for example, 2 rectangles, I get an approximation that looks like, something like this. So I'm approximating the black area by this red area. And there's some error, right? Like I'm sort of underestimating here, and I'm overestimating here, and so there's some error here. And if I want to get a better approximation, I could use more rectangles. So if I have my function like this, if I use a lot of rectangles, so maybe I chop this up into 100 or 1,000 rectangles, then my rectangles look very close to the function value. So it kind of looks something like this. And there's not a lot of space between the curve and the rectangles. So the more rectangles I use, the less space there is between the area that I'm approximating with the red rectangles versus the black shaded area that I'm actually trying to evaluate. And so this error is going to get better and better. So the approximation is better the more rectangles you use. Okay, and so we can define the area to be what happens when I take the limit of this process. So I'm gonna, for any fixed n, I get an approximation. The larger n is, the better my approximation is. And so I'll make the definition of area to be the limit as n goes to infinity. So this is going to be the limit as n goes to infinity of this formula, exactly this formula. So it's b minus a over n times this, the first height plus the second height plus the third height, etc., plus all the way up to the nth height. And that's the definition. So if this limit exists, we say that is the area. As the number of rectangles here goes to infinity, the area that's given by these rectangles is becoming a closer and closer approximation and converges to the actual area under the curve. Okay, so whenever this limit exists, we call this the area. Again, this is for the moment only when f of x is positive. Okay, so I'm assuming f of x is positive, and this is sort of a confusing limit. So we write down different notation for it. It's sort of the same as like when I defined the derivative, it was this difference quotient, and to make our lives easier, I made notation that this limit, when it existed, we called it f prime of c. So the same thing's going to happen here. I have this approximation, and I take the limit, and I define this to be my area. And whenever this limit exists, I use the following notation, that this is the integral from a to b of f of x dx. Okay, so this is notation that means this. It means exactly what I've written down right here. So there's several pieces of this. The first thing is that the dx tells me that x is my independent variable. Sort of the same as like when I take the derivative with respect to x, I use d over dx. So this x tells me what the independent variable is. And then the upper and lower limits of integration, so the a and the b, that tells me that I'm integrating from a to b, okay? So that tells me like which width I'm interested in. And then this f of x, that's the function that I'm interested in. So this f of x might change depending on if the function changes. This is called the definite integral. This is the definition of the definite integral, and this is the definition of the definite integral of f of x from a to b. So this limit itself is a definite integral, and the specific function we're interested in is this one, f of x, and the specific interval that we're interested in is a to b.